Hello students, welcome back to another class. Now in the screen you can see a beautiful portrait of somebody. Who is this? So if you know who is this is basically a quiz that we ask. This is a very important favorite question of mine when I design medical quizzes, right? So if you know this, you can simply pause this video and you can write the name or what I am talking about in the comments, right? So even if you don't know, it's fine because it's my job to tell you. Okay, fine. So let's keep the suspense and let's move forward. So as I told you, today we'll be discussing a very common topic, most of which you already know, right? So only if you come across something which you don't know or something conceptual, then only you can even bother to write. So our topic, and she is keenly related to enzymology, right? So we will be discussing enzymes today. Yes, I know you have been taught very well, but there may be few key areas where the concepts might be not clear, and personally I love teaching enzymes, so it was already completed before I came to know you guys. So here we go. Now this time enzyme is elaborated in competency 2.1. If you see the competency booklet of MCI, you can see the first competency 2.1 tells you about what you need to know, that is the fundamental concepts of enzyme, isoenzyme, alloenzyme, coenzyme, cofactor, and enumerate the main classes of IUBMB nomenclature, right? Then immediately next they give a practical. Observe the estimation of SGOT and SGPT. So it's a demonstration class, okay, it's not a lecture. But everything else is again lecture. So describe and explain principles of enzyme activity. Over here you get the regulation of enzyme activity. Describe and discuss enzyme inhibitors, right? Then diagnostic isoenzymes, right? See clinical utility of various enzymes, and discuss the uses of enzymes in laboratory investigation. And lastly, interpret laboratory results. So we will be giving you flashcards which will contain the patient parameters, and based on that you need to analyze your results. So all of them are now a part of syllabus. But most importantly, the long theory question will come from 2.1, 2.3, 2.4 and 2.5, and to some extent short note in 2.6 as well. These two are mainly practical session. If you are facing a clinical based question may also directly come from 2.7. all right. So we will start with very basics. Now let me tell you, we will be covering all of them in many part lecture series, all right. So from today, whenever I have a class, I'll be covering all of these in small sessions, right? So at the end you'll be calling me enzyme sir. So as you know, all enzymes are protein. The exception is ribosomes. So ribosomes can also act as enzymes, and in that case they are known as ribozymes. So this is very well known. So how an enzyme molecule is organized, right? So enzyme molecule can have a single unit, or it can be a multimeric enzyme. You have already read example of enzyme that has got multiple subunit. Those are known as complex, right? So you have read fatty acid synthase complex, alpha ketoglutarate dehydrogenase complex, all right? PDH complex, I mean pyruvate dehydrogenase complex. So those are actually multimeric enzymes. There is an explain why type of question that you need to answer. Okay, this comes very frequently. It says the catalytic activity of enzyme depends on the integrity of its native conformation. Simple explain why type of question in our university, it comes as the last question, often without any alternative. So this is one of the most common questions that we will find from the very basics. The catalytic activity of enzyme depends on the integrity of its native conformation. So what will be the explanation? The explanation is basically very similar. It's the nature of the enzyme that dictates its function. As soon as you detach the enzyme from its coenzymes or functional subunit, or even if you break down the enzyme to its component amino acid, everything will be gone. So basically, it's the nature of the enzyme which says the catalytic activity of the enzyme is lost if. So what are those ifs? If an enzyme is denaturated or dissociated into its subunit. So if a multimeric enzyme is dissociated into its monomeric subunits by heat or by extremes of pH, any denaturation, any reagent or a condition that will cause denaturation of proteins, the enzyme activity will be lost. Not only that, if an enzyme is broken down into its component amino acids, that is single subunits, the enzymes will also lose their function, right? So thus primary, secondary and tertiary and quaternary structure of protein enzymes are essential to their catalytic activity. So the proper final three-dimensional tertiary or quaternary structure is most important. Otherwise, enzymes will not function. The moment we break down an enzyme into its simpler form, the activity or the function of that protein will be lost. So let us introduce yourselves with few terminologies. All right. Proenzyme, right? Proenzymes or zymogens are the enzymes that are not yet active. They are something before they come into their active form. You already know a few examples of proenzymes, especially in our digestive system. Pepsinogen, trypsinogen, right? Those are proenzymes and they need to be activated by either HCl or CCK, those intermittent enzymes, so that they are converted into their active form, trypsin, chymotrypsin, like that, right? So they are proenzymes or zymogens. The next key concept is about cofactor, right? So what are cofactors? These cofactors are components of enzymes that are basically non-protein part of enzyme, right? They are related to enzyme, they are essential for catalytic activity, but the key highlight over here is non-protein. Okay. So cofactors can be of two types. There are much confusion in many students about cofactors, coenzyme, prosthetic groups, etc., etc. So often examiner will may try to confuse you. Okay, how coenzyme is differing from cofactor? Is coenzyme a part of cofactor or cofactor is a part of coenzyme? So make all the concepts clear right now. So cofactor is the bigger thing. It's a non-protein molecule, right? Essential for catalytic activity. Now cofactors can be of different types. It can be a non-protein organic molecule, or it can be a non-protein inorganic molecule. Mainly the non-protein inorganic molecules are metal ions, mainly. And the non-protein organic part are coenzymes. So basically coenzyme is a cofactor, right? Now what is the prosthetic group? Prosthetic group is a cofactor, all right. But generally coenzymes are loosely bound to the enzymes, but prosthetic groups are covalently bound to the enzyme. They are very strongly bound to the enzyme. So cofactors is the big thing. They consist of prosthetic group, they consist of coenzyme. Generally coenzyme is non-protein organic, and anything other than non-protein organic is not coenzyme. They are cofactor. That can be metal and they can be other prosthetic group, for example vitamins, right? So coenzymes are non-protein organic. These two are keywords you must mention, right? So see, prosthetic groups, coenzymes or cofactors that are bound covalently to enzymes, very important. So prosthetic group can be organic or prosthetic group can be inorganic, but the difference lies over here. See, cofactor can be classified based on their chemical nature into coenzymes and non-coenzyme. Coenzyme is the organic part and non-coenzymes are mainly the other cofactors that can be metal ions, or they can be prosthetic group. If they are prosthetic group, then they are covalently bound, right? So there is an overlap between coenzymes and prosthetic group. Okay, if something is organic and it is bound so tightly that the enzyme will denature if we try to separate, then that is actually a prosthetic group. Otherwise, coenzymes like NAD, FAD, those are organic but non-protein, those are loosely bound. Okay, so these concepts, it should be very clear for Viva. Next are apoenzymes and holoenzyme. Apoenzyme is basically the incomplete enzymes or only the protein form of enzyme. When we add the apoenzyme with a cofactor, the whole functional unit is completed, then we get holoenzymes, right? So these are few basic terminologies that should be very clear. Okay. Next, when we consider about metal, as a cofactor, depending on the type of enzyme, the enzymes that are acting in conjunction with any metal ions can be of two types. They can be metal activated enzyme or metallo enzyme, right? So we will see one by one. What are metal activated enzyme? It means these enzymes show a greater catalytic activity by the presence of a mono or divalent metal ion exterior to the protein in the assay medium. What do we mean over here? Even if the metal is not present, there will be some minute amount of catalytic activity. There will always be there. But if the concerned metal is present, it will hugely amplify the catalytic power of the enzyme. Alright. Metal activated enzyme typically lose activity during purification. Okay, this is an analytical property. For example, hexokinase requires magnesium. Another enzyme that has been taught very recently in molecular biology that requires magnesium is Taq polymerase. Okay, TAQ, Taq polymerase. So Taq polymerase is a normal DNA polymerase that has got a very low polymerizing or amplifying activity. But if we add a certain amount of critical magnesium ion solution, its activity increases manifold, and thus it becomes a metal activated enzyme. So how is it different from metallo enzyme? Metallo enzyme are metal as cofactor bound firmly to a specific region. So in this case, the metal is actually the prosthetic group, right? For example, cytochrome oxidase contains iron and copper. In this case, metal ions cannot be separated without molecular breakdown of the enzyme, right? The enzyme structure will be broken. Catalase contains iron. So you know the structure of cytochrome. It has got an iron in the center and 4 cytochrome pyrrole ring like that. And just give you an example. If you look at the structure of hemoglobin, same cytochrome. So we cannot remove this iron. We cannot simply just remove this iron just like we can do from hexokinase. Hexokinase is associated with magnesium, but we can remove the magnesium. It will lose their activity. It will lose their major catalytic activity, but it will be still in the hexokinase form. It will still remain as an enzyme. However, if we remove iron from cytochrome oxidase, the structure will simply disrupt. So this is the difference between metal activated enzymes and metallo enzymes. Next we come to IUBMB classification. The IUBMB stands for International Union of Biochemistry and Molecular Biology. Now they actually classify enzyme based on this type of nomenclature, A dot, B dot, C dot, D, and these are actually represented by numbers, right? So enzymes basically are classified according to the type of reaction they catalyze depending on their properties, right? This is the very famous classification that you already know, and it's given in almost all textbooks. The mnemonic is OTHLIL, OTHLIL. So class 1 basically is oxidoreductase group of enzyme, then transferase, hydrolase, lyase, isomerase and ligase. I will not be going into the details because this is very basic. You can pause this and you can read from here, you can read from your textbook, but know this, at least 2 examples of each should be known at your fingertips. Alright, the moment examiner asks you, okay, name some lyase enzyme, you must be able to tell aldolase. I'm just giving you an example, okay? And a separate class has already been taken on oxidoreductase group of enzyme. So all of this can be asked in Viva, but together oxidoreductase enzyme will again come as a short note. Alright, so be very careful about oxidoreductase enzyme because they have got various subclasses. So today we will be focusing, for an example, hexokinase, the enzyme that you know, the first step of glycolysis that converts glucose to glucose 6-phosphate. The IUBMB number of that enzyme is 2.7.1.1. So what are these? What do they stand for? This will be asked in Viva. So this number 2, the first one is class. So class 2 means OT, T for transferase. So hexokinase is a transferase group of enzyme. The next number, that is 7, is subclass. So what is this subclass of transferase? The subclass transferase transfers a phosphate group. There are multiple types of transferase enzyme, but especially the enzymes that are transferring a phosphate group. So glucose to glucose 6-phosphate. One phosphate group has gone and has been added to glucose. So that is class 7 of class 2. So 2.7. Next, very important, the first subclass in which the acceptor of phosphate group is alcohol. So where is the alcohol in glucose? Yes, there is. It's a polyhydroxy aldehyde or ketone, right? So polyhydroxy alcohol. There are multiple OH groups in glucose, right? Glucose, fructose, everything. So the first is a CHO group and the rest are all OH, right? So polyhydroxy, hydroxy in organic means alcohol. So the acceptor is actually an alcohol. So that class of enzyme, that is the subclass of class 7, not only transfers the phosphate group, the transfer actually happens to an alcohol group. And next, and there are multiple type of enzyme that are doing this. So we need a subclass. Okay. So that is the first enzyme of the first subclass. So you can ask me, so what are the, so if this is so unique, what are the other enzymes? For example, you can Google it. You can research all you want. 2.7.1.2 is glucokinase, right? 2.7.1.3 is ketohexokinase. 1.4 is fructokinase. 2.7.1.5 is rhamnulokinase. Okay, so just you can do your own research and you will find even this subclass is not enough to classify those enzymes. So if we make 4 classes, we can get a unique idea what is this specific enzymes we are talking about, right? So next we start our journey into enzyme kinetics, right? So basically what is kinetics? Kinetics is the study of the rate of enzyme catalyzed reaction and the factors that influence the rate of enzyme catalysis, right? So there are few concepts, that is the energy barrier. It means a substrate A has to be converted into a product B, right? But if the reaction was so much spontaneous, the Gibbs free energy would have been negative, then we don't need any enzyme at all, right? Basic rule of thermodynamics. But there is an energy barrier that is preventing a compound A to become compound B, right? And enzyme actually catalyzes that, right? So there is an energy barrier and there is an activation energy with which an enzyme needs to start a reaction, following which the energy will be lowered. There will be a transition state that will be reached, an enzyme substrate complex, and then ultimately the product will be formed. So how do enzymes work, right? Basic principle of enzyme action which is known to all, that is, I already told you, enzyme substrate complex formation, which is reversible, very important. ES, there is no covalent bond. So this is an MCQ question, right? Enzyme substrate bond can contain all of the following interaction: electrostatic, yes; van der Waals, yes; non-covalent, yes; but covalent, no, right? So by weak non-covalent interaction. So when they interact with each other, they release a small amount of energy, and thus after the energy is released, then the binding energy is actually lowered, and this is used to lower the activation energy. Basically, normally the product A cannot be converted to product B because it needs a very high activation energy. Enzyme, when it reacts, it will simply lower the activation energy. You have already in your chemistry classes, you must have read how oxygen is produced, and which the first concept of catalysis comes from there. MnO2 is a catalyst. So there will be no reaction if you keep on heating potassium permanganate or anything. But the moment you add MnO2, it will lead to profuse generation of oxygen. Anyway, so see, these are the areas, the questions that will be asked in Viva. So this is the checkpoint. So what is enzyme? Okay, you need to define an enzyme. Nomenclature of enzyme, IUBMB nomenclature, very important. Classification of enzyme with example, all the 6 classes of enzyme, very important. Structural organization of enzyme, it means apoenzyme, coenzyme, holoenzyme, and multi-unit, multi-subunit enzyme, right? Specifically, they can ask you what is holoenzyme, what is apoenzyme, what is prosthetic group, what is metalloenzyme, what is metal activated enzyme, and mechanism of enzyme action and factors affecting enzyme kinetics and enzyme reaction, that I will be discussing very soon. So what are the mechanism of enzyme catalysis? Enzyme catalysis basically depends on the availability or the conformation of the active site of the enzyme. It was not known when enzyme research started, but slowly and steadily we were much acquainted with the active site, that is also known as the catalytic site. So what happens? That is the site of an enzyme where substrate will come and bind, right? Very basic concept that you have been taught over and over again right from your basic science lesson. So this active site, there are few properties. What are the properties? These active sites are substrate specific. For example, if I am glucokinase, only I will bind to glucose. My active site can bind glucose. Fructose, if comes, it cannot bind. Similarly, if I am fructokinase, I will only allow fructose to bind to my active site. Glucose will not be binding, right? There are few enzymes, for example, hexokinase, that are a little bit liberal. Their site are also substrate specific. For example, any hexose sugar can come and attach, but not any pentose sugar. Hexokinase will not catalyze ribose 6-phosphate formation, ribose 5-phosphate formation. So these are the few characteristics extremely specific for substrate binding. And how are they specific? In most textbook, you see a 2-dimensional diagram, the lock and key model, all that. A square diagram, an enzyme like this, and substrate which looks like this. Basically, it's not that 2-dimensional, the whole thing, a 3-dimensional structure. Basically, it's a hole or a crevice, okay, a crack. That crevice is actually occupied by a substrate which is actually a non-polar. There are no interaction or electrostatic interaction. Substrate can come and bind only when the reaction is about to complete. Mind it, I already told you, enzyme substrate complex are weakly bound by non-covalent interaction, right? It means there is no covalent bonding at the active site till the enzyme is there in the enzyme substrate complex form. You know the reaction enzyme plus substrate, it forms an enzyme substrate complex, and then ultimately we get back the enzyme and then we get the product. So when the reaction is about to complete, then there are some covalent binding. So enzyme substrate complex formation are of two types. The model, right? So there were two models that were hypothesized how the enzyme substrate complex formation can happen. So they are the Fisher's lock and key model and the Koshland's induced fit model. Each of them will come as a short note and will be asked in Viva, right? So let us first discuss about Fisher's lock and key model. Emil Fisher, the famous Nobel laureate and chemist, what he proposed is the active site of the enzyme is very rigid and it actually looks like the substrate and it's a pre-shaped template. For example, if my enzyme looks like this, the substrate has to look like this. So it's a pre-shaped template. So enzyme already knows that this substrate will come and bind over here. So if the substrate is not the exact shape as the enzyme, the reaction will not happen. So it's a rigid, the conformation cannot change, right? So already in proper conformation, even in absence of the substrate. So even if substrate we do not give, the enzyme will continue to remain in this, in weight, so that one substrate which is exactly fitting the structure will come and bind over here, right? So substrate comes and fits in the active site of the enzyme just like a key fits in a lock, right? So structural complementarity. So basically it will exactly fit like this. So this is the concept, this was the concept of Emil Fisher and lock and key model. However, the most difficulty or the need of another model, or why this model was not widely accepted or applicable, was the phenomena of allosteric regulation or allosteric inhibition, right? So important, remember this is a very important catch Viva question. Fisher's lock and key model is fine, it can explain many things, it can explain many mechanisms of enzyme catalysis, covalent catalysis, metal ion catalysis, but it cannot explain allosteric. So examiner will ask you exception to Fisher's lock and key model. The moment he asks you, you must tell, sir, allosteric modulator. So allosteric enzymes cannot be explained by Fisher's lock and key model, and then we need Koshland's induced fit model. So what does the induced fit model, how does it differ from the lock and key model? Koshland told that enzyme don't need to be rigid, it's like a dough, it will mold itself. So active site conformation is flexible and dynamic, okay, it can change. So enzyme, so substrate binds to the enzyme and forms enzyme substrate complex intermediate, okay. Mind it, the enzyme substrate complex intermediate, which is formed by non-covalent bond, was first hypothesized by Koshland's induced fit model. Fisher always told that enzymes bind so strongly that they are so close to each other that there are covalent modifications and covalent binding. Unless there is covalent binding, an enzyme and substrate cannot come and close to each other in a structural complementarity. We are talking about induced fit model now. Next, what happens? Both are dynamic. So substrate binding to the enzyme. Mind it, the enzyme doesn't look like the substrate. However, the substrate can induce. Both can induce into each other actually. Substrate binding to the enzyme induces a conformational change in the active site to attain the final catalytic shape. Converse is also true. The enzyme in turn induces a reciprocal change in substrate to alter the configuration to the transition state. So both enzyme and substrate, they don't look like each other to begin with. However, they come and interact to form an intermediate complex. Thereafter 3D conformational changes happen. So substrate is inducing some change in the enzyme, enzyme is inducing some change into the substrate, and then they both bind. You see this example, this substrate is looking like this, but the enzyme active site is not looking at all like this. Then there are changes, now the enzyme active site molds into the complementary structure of the substrate, and then substrate can bind. Mind it, the reverse, that is the changes induced by the enzyme to the substrate, is not that much. Otherwise, the substrate would have changed. We cannot make a glucose into fructose and then react, right? So the change in substrate is minimum. However, the change in the active site of the enzyme is huge. Therefore, it is not at all rigid, and this is how induced fit model differs from the lock and key model, right? So now we look at the factors affecting the rate of enzyme catalyzed reaction. 10 minutes left. So these factors are, number one, temperature, right? So you will get question, explain what type of question. Each enzyme works in an optimal temperature or narrow range. Explain. What you will have to say? First, you need to tell about the nature of proteins or the nature of enzyme, that they are proteins. Excess heat will lead to denaturation of proteins, right? However, it is true that activation energy, right, is also increased as we increase the temperature gradually to a certain extent. So till activation energy, activation energy is lowered if we give external energy. So up to a certain extent, increase of temperature will lead to increase of enzyme function. So initial increase in temperature, enzyme function actually increases. However, then it reaches a limit. So that limit is known as the optimal temperature at which the activity of the enzyme is maximum. Thereafter, if we further increase the temperature, the activity will be lost, right? So the enzyme will fully cease to exist. And you know, the temperature and these type of questions, in these type of question, factor affecting enzyme activity, you must give curves or graphs. So substrate concentration, temperature, pH. Generally, in case of temperature, it looks almost the same in case of all the factors that's important to you. So first, the enzyme activity will continue to increase, then it reaches an optimal temperature at which the enzyme activity is maximum. So this is the temperature, or this is the temperature, this is the enzyme activity, and after which the enzyme activity will simply fall, right? So, and after you write this, since this question is demanding an optimal range of temperature, you must mention few enzymes that are exception. For example, few enzymes that are also active in very high temperature. For example, Taq polymerase in case of PCR. So you must mention factors affecting enzyme activity as a miscellaneous or as a exception, or as a special case, you must mention Taq polymerase. Rest is all the same thing. There is an optimal pH till which an enzyme will start to show maximum activity, and after that pH is reached, if you further increase pH, the activity of the enzyme is will fall. So if this is pH and this is the activity, it will look like the same bell-shaped curve. Same with enzyme concentration and substrate concentration. Now these two are actually critical. It's not exactly the same. Over here, you need to read something that is known as order of enzyme activity or enzyme reaction order. It means zero order reaction, first order reaction, so on and so forth. Let me tell you in brief. A zero order kinetics or a zero order reaction means no matter how much you increase the substrate concentration, it can be done if we are focusing on enzyme concentration or we are focusing on substrate concentration. But when you are seeing one, the other should be fixed. For example, over here enzyme concentration is fixed and we are now increasing the substrate concentration, we are altering the substrate concentration. So if this is the enzyme activity, right, and if this is the substrate concentration, so this is enzyme and this is substrate. In case of zero order, what will happen? No matter how much we increase the substrate concentration, the curve will look like this. it will be an absolute parallel to the baseline. It means the enzyme will simply attain its maximum activity and the further change will not happen even if we increase the substrate concentration. What is first order? First order means the enzyme activity is linearly related to substrate concentration. So, if this is the enzyme and this is the substrate concentration and this is the enzyme activity, the curve will look like this. So, if you give twice the substrate, the enzyme activity will be twice. So, remember, rate of change of reaction is independent of substrate concentration in zero order. So, this is zero order, important MCQ and Viva question, and rate of enzyme reaction is directly proportional to the substrate concentration in case of first order kinetics. Okay. So, there are of course second order, third order in which reaction will look like parabola and hyperbola. It's not important for you guys, but what's important is, it's a homework. You can write in the comment or you can type in the chat group that example of two enzyme that follows zero order kinetics and example of two enzyme that follows first order kinetics in our body. Okay. So, in the next class, we will be discussing about, we will start the enzyme kinetics, what is steady state, what is pre-steady state, how does Michaelis-Menten equation comes into existence, and how we can actually interpret various type of inhibitions. Alright, so the whole thing will be discussing in next class, and yes, the answer to that first portrait of the lady is Maud Menten. Okay. So, so here we come to the end of our class. The further parts of this lecture series will be linked in the video description. So, feel free to watch them all. Feel free to post your comments, and I will see you soon in the next class. Till then, bye and take care.